All right, fun facts about magnetic fields. Fun fact number 1. What happens if you take a magnet and you break it in half? Well, I'm going to show you. Here, I don't like this marker. I like this marker. Right, way better. Here I have a magnet with a north and a south pole, okay? And I decide I'm going to take this magnet and I'm going to snap it in half and I get this sort of thing, right? Okay, so this is still going to be a north pole and this is still going to be a south pole. But the mere fact of breaking a magnet in half means now that I have 2 magnets that are half the strength that they were before. All right? Now, what happens if I snap these 2 magnets in half and now I have this situation? All right, you guys know I have a problem with drawing, so. You, of course, then get 4 magnets, a quarter of the strength of the original magnet. All right, this will keep on happening down and down and down until you have smaller and smaller and smaller and smaller magnets. Because you may know that all atoms have a certain electron orbital momentum, right? It's also known as angular momentum. And so that angular momentum of an atom is ultimately what causes there to be a magnetic field inside of different materials. We're going to explore more about that as we go on in the chapter and why that is, right? But it comes down to the fact that moving charges actually create magnetic fields. So if you have an atom right here, right, and an electron zipping around it, right? Quantum mechanically, that's not exactly what's happening, but we can approximate it in a classical sense. That's what's happening. You have this electron whipping around this. That is going to create a magnetic field that comes out like this, like a little bar magnet, out and then back in again. Okay, so this is like a little north pole and a little south pole. All right, so if you keep snapping the magnet, snapping the magnet, snapping the magnet smaller and smaller to the point where you get to one single atom, you still have a magnet. One atom, because it involves a moving charge, is actually one tiny, tiny indestructible, not indestructible, but it's the smallest component possible of a magnet. You could actually even get a little bit smaller than that when you look at a single electron and you see that it has spin. Okay, so you probably have heard of this idea that electrons have spin. So if you think of that as a charge rotating, okay, again, quantum mechanically, that's not exactly what's happening, but we can look at it that way in a classical sense. That's still charge moving because it's spinning around some axis, and that electron will still create some small trace of a magnetic field. So really, really cool. If you break up a magnet on and on and on and get smaller and smaller and smaller, you get more and more magnets until you get to a single atom. Cool. All right, fun fact about magnets too. Okay, so in the electron world, we have protons and electrons. Those are called electric monopoles. Okay? In other words, you have a proton, an electron, and the field lines leave the proton and end up on an electron. Okay? You don't have similar things for the magnetic world, right? You don't have, and this is really, really cool, you don't have like a north particle and a south particle, right? Where like the north leaves and ends on the south. You don't have that. You just have these bar magnets, right? Where you have these objects that are connected and a north pole leading to a south pole. In other words, there's no magnetic monopoles. Okay? If we were able to ever discover one, if you someday were ever discover a magnetic monopole, you would instantly win a Nobel Prize. It'd be just an enormous discovery. Okay? But for now, there isn't any, and that means that the magnetic world is going to look a little bit different from the electric world. Okay, and we're going to see some ways in which those differences arise. But you can, the bottom line, the thing that I want to share with you is that you can never have an isolated north pole, and you can never have an isolated south pole. In the magnetic world, they always come together. They always live together. They exist together. All right. So all magnetic fields are caused by magnetic dipoles. All right, that's fun fact number 2. I want to talk a little bit about what magnetic field lines look like, so you can actually check this out on this slide that says, what do magnetic fields look like? And there's a few rules. As you can probably imagine, and definitely can see if you're looking at this picture right now, it is that south and north. Okay? It is that magnetic field lines leave north poles and enter the south poles. Okay? We've talked about this a few times already. And so this south pole will actually go woo, leave, and then come back to the north pole, right? Actually, lied. Leaves the north pole, enters the south pole. Again, enters south pole, leaves the north pole, will always come back to the south pole. You get the idea. Okay? So kind of similar, or at least analogous to electric field lines, but again, you only ever see them together. You don't see an isolated north pole and an isolated south pole. Okay, so always point from north pole to south pole. 2, unlike electric field lines, they are always closed loops. Okay, so what do I mean by that, right? So what's actually happening here? If you were to trace these field lines, this continues on and on through the magnet itself. Okay, leaves, comes back, goes back into the south pole, and then goes all the way through until it's connected. So magnetic field lines, I said that there's some consequences to there being no monopoles. So typically monopoles originate charge or field lines, and they disperse or they diverge from those poles, right? From those monopoles. But if you don't have a monopole, all field lines have to be closed loops. All right. So if I take a look at one individual magnet, so let's take a look at one individual magnet like this here. Okay. Every time that I have a magnetic field line that leaves a pole and comes back to the south pole, that field line continues on through inside the object itself and continues in a loop. And so same thing. On the other side, those field lines always just continue. When you're talking about magnetic field lines, you're always talking about closed loops, unlike a electric monopole, which originates field lines, and those will go on and continue and continue and continue forever. All right? Hope that makes sense. So that's rule number 2 about magnetic field lines. Rule number 3 is that field lines are closest together when they're the strongest. So stronger field lines happen when they're closer together. That's also the same for electric field lines, so that also makes sense. I also want to be clear that the SI unit for a magnetic field is the Tesla. Okay, so that is just notation T, and that is the unit, the SI unit for a B field. Magnetic fields are also called B fields, right? Whereas electric fields are E fields, magnetic fields are B fields. Why exactly is that? Again, it's an interesting history of physics question. Well, like, why is it not M field and E field? And I invite you to explore that and write me back if you have an answer. All right. Do I want to add anything to that? I don't think so. So I'm going to move on to, if magnetic monopoles don't cause magnetic fields, then what does? If you guys can go to that slide. You know the answer to this. Tell me the answer. If you've been listening so far, you know it is because of moving charges, right? Moving charges cause magnetic fields. Okay, so what is a classic example of a moving charge? Well, classic example of a moving charge is a current, right? You have lots and lots of charges moving, right? So if I have a current going up here like this, right, you actually get magnetic field lines. Now, what do those magnetic field lines look like if you have a straight current moving like this? Okay, so in the realm of magnetic fields, there's something called the right-hand rules. You may remember it a little bit from last semester, but there's some nuances to the right-hand rule for magnetic fields. And there's actually a couple different right-hand rules. So I'm going to start by saying that the first right-hand rule in the world of magnets is that if you take your hand, your right hand, okay, and you take your thumb and you point it in the direction of the current, then your fingers will wrap around in the direction of the magnetic field. Okay? So once again, I take my thumb, I ask myself, what's the direction that the current's moving? Is it going down or is it going up? No, it's going up, right? So up, and my fingers then will wrap around the wire, and that is the direction of the magnetic field. So you have magnetic field lines that surround then, going this way, behind and coming back in front, okay? You have magnetic field lines that surround this thing, right? And do you still have magnetic field lines over here? Yes. Like it'll be weaker, but yes, there's magnetic field lines. These are concentric circles, as you can see from this picture, that wrap around at all the different radii, okay? And so how do we actually calculate that magnetic field at a given radius? And that is actually very easy. There's a formula that we can use. I'm not going to derive it. I'm going to give it to you for now. But this can be very easily derived by something called Ampere's law. But the magnetic field due to a long straight current carrying wire is just equal to this symbol called mu naught, which is the magnetic permeability of free space. So this is kind of analogous to the epsilon naught in the electric world, but this is for the magnetic world. Okay? So permeability of magnetic field in free space, and that is equal to 4 pi times 10 to the minus 7. Okay? I, which is just the current, it's a lot we've been using capital I, so I'll keep going with that, over 2 pi r. That's it. So if you want to find the B field at any radius away from a long straight wire, so this is just for a long straight current carrying wire, as opposed to a loop of current, right? Then the formula is just the permittivity of magnetic field in free space, 4 pi times 10 to the minus 7, times the current going through that wire, divided by 2 times pi times however far you are away from the wire. So r is the distance from the wire. So using this, we can find the magnetic field a distance from any current carrying wire. And you'll find out that that's actually very powerful, not just in the world of, of the gadgets that kind of function our world, but also in the realm of life. And in the next example, we're actually going to see that firsthand.